And in quantum field theory, the problems are typically given in terms of renormalization group flows. What I mean is that the problem is a theory defined as short distances, and solutions are their behavior at long distances. And keeping track of this scale dependence is called renormalization group flow, or RG flow. And since many of you may not be working in high energy physics, I'd like to give you one similar situation in our daily lives. And this is one of the most famous drawing in Japan. And then you may know that the particles in the paint determines the colors. So they determine which light to reflect and which light to absorb. But we are usually not interested in this phenomena at small scales. We are interested in the larger scale, what this drawing expresses. And we do a similar thing in high energy physics. So the problems are defined as short distances, and then we are interested in their behavior at long distances. And this is one example. In this case, the theory is defined as SUN Yang-Mills theory. And then in order to make this problem interesting, I think one parameter in the theory, theta equals to pi. So this is our problem. And then we ask what this theory does at long distances. And then these people argue that this theory is gapped, and CP symmetry is spontaneously broken, and it is confined at long distances. So when we say possible answers, we mainly use two criteria. One is about gap, and another is about symmetry. The long distance theory can either be gapped or gapless. Gap theories are described by topological quantum field theory, and gapless theories are usually described by conformal field theory. And symmetry can either be preserved or spontaneously broken. So our job in quantum field theory is to identify in which quadrant a given UV symmetry belongs. And also, as one terminology, if all symmetries belong to here, namely gapped and preserved, we say it is trivially gapped. And the example I showed says the following. First, it is believed to be gapped, so we use the left column. And then the confinement is defined by preserved one-form symmetry. So we put confinement here. And also CP symmetry is believed to be spontaneously broken, so we put CP symmetry here. So if you could show this behavior, and then you say this theory is solved. And here's a brief review of their argument. The system is given by this action function. The details are not important, but the important thing is that if you take this theta equals to 0 or pi, this is the theta parameter, and then the system has CP symmetry. And also for any theta, the system has a ZN one-form symmetry. And what they found is that these two symmetries have a mixed foot anomaly, or theta equals 0, so theta equals pi. And then if there's an anomaly, then we cannot have a trivial gapped phase. So if we go back, all symmetry cannot be here. So one symmetry should be spontaneously broken. And then assuming the confinement, and this means the preserved one-form symmetry, the other symmetry, namely CP symmetry, should be spontaneously broken. This was their argument. And the key point in this analysis is that we use symmetry and its two-foot anomaly to constrain long-distance behaviors. However, the definition of symmetry was generalized in this paper, and then the general symmetry is given by monoidal category. Monoidal means you have a product. And in this categorical language, the two-foot anomaly is part of the data of this monoidal structure of the category. However, general symmetries often have additional structures. So the natural question I'd like to address in this talk is this one. The additional structures of symmetries impose new constraints on RG flows. So this is a question I'd like to address in this talk. And in order to do this, I follow this content. So first review the general symmetry, and then next I discuss the new constraint on RG flows. And if time permitted, I will discuss one example. So let's start from the general symmetry. So as I mentioned, the general symmetries are described by monoidal categories, but if you consider finite symmetries, it is in general given by fusion category. And one easiest way to understand fusion category is its analogy with representation. So in order to make this very concrete, let's consider SU2 group, and let's consider two-dimensional irreducible representation, IREP. And you know that you can take a tensor product of these IREPs, and then you get a four-dimensional reducible representation. And since this is reducible, you can decompose as a direct sum of IREPs, and you get one-dimensional and three-dimensional IREPs. And if you look at this equation, you find the irreps are equipped with two binary operations. One is tensor product, and another is the direct sum. And similarly, fusion category C has simple objects. This corresponds to irreps. And then they are equipped with two binary operations, fusion product and direct sum. So I'd like to take this as a working definition of a fusion category in this talk. So the important point is that you have simple objects and you have two operations. And here is one example. This is called Ising fusion category. And it has three simple objects, one, x, and y. And they are equipped with fusion product and direct sum. And the fusion product looks like this. If you use f, x, and x, you get 1. If you are familiar with critical Ising model, this is the Z2 symmetry of the model. And if you fuse x and y, you get y. And if you fuse y and y, you get a direct sum on 1 and x. So this direct sum shows this is something beyond the group-like symmetry. And as I mentioned, fusion category C may have additional structures. And one important structure in this talk is called braiding. And this is, so if you have a fusion C1, C2, then you can exchange the order of these two objects. So braiding sends C1 times C2 to C2 times C1. And if a fusion category has a braiding, this is called braided fusion category. And these braidings are characterized by some real numbers called Kohman dimensions. And one example is this. So if you take braiding twice, the order becomes the original one, and it simplifies. And then the formula is given by this. And C1, C2, Ck counts the number of simple objects Ck in this fusion C1 times C2. And this IDCK is the identity morphism at Ck. And this H1, H2, Hk are Kohman dimensions. So in this way, these Kohman dimensions characterize braidings. So next we discuss additional constraints imposed by these braiding structures. So an RG flow preserving a fusion category CUB is a monoidal functor from CUB to CIR. Here, monoidal means it preserves the product. So this is a generalization of a group homomorphism. So I think you cannot see, but I wrote something here. And because this is monoidal, CIR is the same as CUB as a fusion category. And the question is, what is the braiding structure of CIR? We know CIR is the same as CUB as a fusion category, but we don't know the braiding structure of CIR. So this is the question. And here we can prove the following theorem. Let CUB be the surviving braided fusion category, and CIR be its image braided fusion category under this monoidal functor. And here is the assumption part. If the RG flow admits RG defect, I will soon explain what is RG defect. And then the result is the surviving symmetry object, CJUB, and its image, CJIR, obey the half integer condition. So these are the Kohman dimensions of these two objects. And then their Kohman dimensions should sum up to half integer. And here is the proof. So first, with RG defect, we have product symmetry object, CJUB, CJIR. And this obeys the trivial fusion with identity, identity. And therefore, we get a disorder operator at the end of this product symmetry object with Kohman dimensions HJUB plus HAR, 0, or the opposite. And I ought to argue that these disorder operators define extended vertex operator algebras. And in vertex operator superalgebras, the weights should be half integers. So these sums should be a half integer, and then we prove this half integer condition. And I have to explain where did we use RG defect. So suppose you have this RCFT UV in the whole two-dimensional spacetime, and then we deform it, and then by assumption, this theory flows to the IR rational combined field theory. But we can modify this operation a bit, and then we leave the left-hand side untouched and only deform on the right-hand side. And then by assumption, the left-hand side remains RCFT UV, but right-hand side flows to RCFT IR. And the system develops a defect, and this is called RG defect. And in this setup, the symmetry object CJUB lives in the left-hand side, and CJIR lives in the right half. So they live in the different part of the spacetime. But we can fold one theory on another, and then get a product theory. And in this setup, the symmetry objects live in the same part of the spacetime, and we can consider product symmetry object. I use this in the proof. And the question I addressed in this paper is that when the sum is half integer and when it is an integer. So if we know this a priori, then we can make the constraints stronger. And the small observation I made in the paper is we found a necessary condition for the sum to be half integer. And here is an argument. The vertex operator superalgebra is based on a super vector space. So it has a Z2 grading. And so these two facts lead to the following logic. If the sum is a half integer, then there should exist a half grade, Z2 grading. So this Z2 grading is a necessary condition for the sum to be a half integer. And the largest grading of this product symmetry, CUB, CIR, is given by the universal grading. And here's the definition of a grading. So G grading of a fusion category C is a pair of a group and the functions from this fusion category to the group, such that if you take the dual, I didn't explain this, but this is very defined in fusion category. And if you take the dual, it is sent to the inverse group element. And it is also consistent with the fusion product. And the universal grading is a universal one. This means for any such pair, there uniquely exists a group homomorphism from UC to G, and this factorizes lambda to lambda C. This is a definition of a universal grading. And here's an example. If you take Ising fusion category, then you can, these are the fusion products, then you can check the universal grading is given by Z2. So this can have a half integer condition. On the other hand, if you take Fibonacci fusion category, you find the universal grading is trivial. So if this survives, then you cannot have a half integer. The sum should be an integer. And you can prove this small lemma. So if you take two fusion categories, C and D, the the fusion category has this universal grading, UC times UT. And you can also, so we are interested in the universal grading of this product symmetry. And then you can compute it as a UCV times UCV. And we know this from just from the UV symmetry. So the necessary condition reduces to this one. So if for the sum to be a half integer, UCUV needs a Z2 subgroup. This is a necessary condition. And since I don't have time, I skip this example. And if you're interested, you can ask. Then I officially get a few more minutes. So what I explained is that the problem in quantum field theory is given in terms of RG flow. The problem is a theory defined at short distances, and then solutions are their behavior at long distances. And in this talk, I limited myself to UV theory is RCFT, and also the IR theory is a rational compound field theory. And here is a more detailed summary. I stop here. Thank you.
Questions? Okay, let's thank Ken now.
That you mentioned, like, and these object can be thought of some quantum fields, like the way you have set up like the X, Y in the Ising model, etc. So is there a way to also like figure out this conformal dimension by these conditions?
Figure out from, so if you have a CFT, then there's something called Moore-Seiberg data. This is a, mathematically speaking, modular fusion category. And then these conformal dimensions are some data associated to this data.
Also, we have to have this HS
That's right.
that defines the CFT.
That's right.
And also, like, would the similar result exist for if we don't have like RCFT, like some IRCFTs?
So you're asking non-rational CFT?
Yeah, because it may also happen some non-rational UV
right.
CFT can
That's
flow
right.
to rational CFTs.
In this talk, I assumed the IR theories are rational. I don't have any results for non-rational IR theories. But UV theory, the assumption UV theory can be relaxed. UV theory can be non-rational.
We can flow to rational
right.
IR theory.
In that case, this theory applies. I believe so.
Okay, let's thank Ken. Stop.